So hopefully you can see my screen
Mm-hmm.
and also my mouse cursor. Okay, so first of all, thanks to colleagues for the interesting talk. I encountered that there are significant differences between DESY or photon science community and so to say the social science. As said, I belong to the experiment control group supporting our beamlines. So in principle, we provide beam time for users, I have to say. And my focus is not so much on sharing data because it's more or less non-existing in the photon science community, rather than already the implications on the data acquisition. Just to see what we are talking about, currently we have, so to say, roughly, depending on counting, 25 experimental stations where we offer synchrotron radiation or synchrotron light to the user community from Germany, Europe, and abroad. And we have several users coming on site carrying out experiments here. So on the one hand, we are just a service provider and have to deal with plenty of amounts of data, so to say, likely compared to social science. Similar to the ESRF, we have different kinds of research and various kinds of beamlines dealing with extreme conditions, which may mean high temperature, high pressure. We have investigations or measurements carried out for in situ studies, seeing what happens on short time scales. We have tomography beamlines, and I'm supervising roughly 20 out of them. We also have colleagues from EMBL, which are doing their stuff by themselves, but nonetheless, we are still in contact. And overall, we have a rather diverse environment, meaning we have various kinds of research. We have different techniques applied during the experiments. We have multiple kinds of analysis. Users come even and provide their own analysis software. And we have plenty of devices resulting manifold kinds of data types and sizes. So just to give you an idea, last year in the period from March 15th to December, we had around 3,000 unique users on site, or unique users, and around 6,500 user visits, which means here all beam time participants, including in-house. Roughly 55% came from Germany, roughly 40 from Europe without Germany, and about 8 to 10% are non-European. And the kind of access, including external stuff, excluding the external stuff, is mainly that we have, on the one hand, on-site users, we have remote users, and we also have a functionality, simply data users. They just like to have access to the data set because they have a common project and they are just doing the analysis without taking care on what's ongoing on-site during the beam time, at least not during the experiment itself. Within the last years, or in particular during the pandemic, data only and mail-in is highly appreciated by our visiting users, in particular that they don't have to handle the experiment, also some kind of stuff, that the experienced beamline stuff is supporting them and taking care on sample alignment and carrying out the measurement in as short amount of time as possible. At the moment, users from overseas have preference for remote access and mail-in. They are not traveling. And typically, an experiment often involves all 3 times of access during this. And given this support for the users, and despite the diverse environment, we can break down our expectations from the user community in principle that they have to deal with. They apply for an experiment, they prepare an experiment, which also means they integrate brought-in equipment by themselves, which means during the data acquisition, we already have to deal with unknown accounts. They are not known to us, they are foreigners, so to say, others, rest of world. They obviously want to carry out the experiment. They want to have access to storage spaces. They want to have access for the users and for the beamline functional accounts. So our experimental stations are still operated by functional accounts, a single account. We have the data acquisition itself, which then implies we have various of formats, sizes, and speed. We have different amounts of data, and we also have to deal with different operating systems, Windows, Unix, Mac. We have activities during the experiment, like data, beside others, data analysis, remote access, or just that the professor at the home institute wants to see what the PhD is doing here. Obviously, we have the end of the experiment where we have to ensure that the data is not accessible for the next user group. And we also have the demand from the users to access the data past the experiment. So not only while it's carrying out, they want to have also offline analysis for on and off site, and obviously also the option to download data. Moreover, we have requests in view of data archival and more, beside common issues like space, performance, and reliability. This is one of our major challenges here, likely which is most significant to social science. From a data management perspective or from the data acquisition perspective, we have, it was already mentioned, the Digital User Office, also part of the experiment control group, mainly by Jan-Peter Kurz, also supervised by Daniela Unger and Ulrike Lindemann from IT, which allows proposal submissions. So in principle, anybody can carry out experiments. The proposals are reviewed. If beam time is granted, the users can do beam time scheduling. They have to declare declaration of substances and list of participants, meaning who is showing up, who should have access to the data. What do they bring in here for the measurements? Various administrative tasks. And from my perspective, most important, and from the data management perspective, while applying for beam time, a so-called beam time application ID is generated, which is a 8-digit unique numbers identifying who is part of the beam time, at what beam line the experiment is carrying out, and when does it take place. In particular, these rather strange demands from the user community also to carry out the experiments with these unknown access, we invented a storage system for PETRA III in 2015. It was invented on the one hand, mainly to deal with the large amount of data, to structure the data that the user hardly can decide how it's organized here on site, and allow to us to provide particular services. Which means we have a directory structure, which we define based on facility and beam time. We have access rights. We have 3 groups per beam time from a unit perspective: a management group, a participant group, and a collaborator group. We have invented an archiving and a portal functionality, which provides 4 user roles. And we have invented a scheme for migration and staging data. We have directory-specific policies, meaning, for example, whether data is being archived, whether data can be accessed read-only or read-write if you want to have analysis capabilities here. And we control the data visibility and accessibility. Given that the beamlines are operated by functional accounts, so to say, 1 account per beamline, we have made the decision to have 2 kinds of storage systems: a so-called temporary storage system, the beamline file system, which ensures the beamline operation itself and carrying out the experiment. It has a limited visibility and it's acting as temporary storage for the beam time and beamline, where we have a concept which is called stop beam time to create this kind of storage provision. And we have a permanent or long-term storage, which is the core file system, which is managed based on ACLs. Everything is based at the moment here on IBM GPFS storage system or IBM Spectrum Scale elastic storage servers. Initially, we invented the system of 55 terabytes based on SSD to cope with the speeds of the detector data. And for the permanent storage, we had an initial size of 700 terabyte based on disk, for it's simply cheaper. Meanwhile, in 2020, we have reached the beamline file system. Serving all beamlines has 220 terabyte total capacity plus additional 220 terabyte disk space. And for the core file system, we are at the moment at 13 petabyte storage capacity total. So the concept with the start and stop beam time is it has 2 arguments at minimum. It's the beam time application ID, the already mentioned 8-digit unique number, and the beamline as cross-check that just to ensure that the beam time, that there is no typo in the beam time ID, that it really matches the beamline. And the script is executed by beamline staff only, and it instantiates the beamline file system and as well as the core file system. So it creates a temporary storage space. and a directory tree in the GPFS core, which the rules and constraints. The beamline file system itself is exported to the beamlines via NFS3 and SMB based on a whitelist, which is maintained by Experiment Control Group. It has a fixed mount point, a fixed visibility at every beamline. And we also have a recommended drive letter for Windows systems in view of coping with performance issues in view of Windows virus scanners and so on. This has rather sloppy ACLs in view that we have user equipment which has come in, which operates on unknown accounts. We have the core file system, which is based on NFS4 and SMB, allowing access from Windows and Unix with ACL control lists and typically cameras. As additional safety measure, we have an ingest of information of the beam time into our Gamma portal. I come to this later. It's mainly the meta information, which allows the users to browse their data to some extent and find what they have carried out so far. Unix groups are created per beam time, 3 in total. And the list of participants denoted or named by the applicants are already copied into the Gamma portal to regulate the access, and also in the ACL list from the portal. And within given limits, it also allows the allocation of compute resources for auto processing. For example, P11, our MX colleague, as Andre has presented yesterday. From a practical perspective, it simply means on the beamline side, left-hand here, we have a temporary storage system with a fixed mount point, GPFS local current, and a predefined directory structure, raw, processed, and shared and scratch, where the beam time data is going in. Parallel, a copy process is transferring the data from the sloppy ACL beamline file system into the permanent storage on ACLs. Also removes the access from the beamline functional account, and only valid DESY account from then on have access to the data here in the GPFS core. Beside the start beam time script, we have a second one, which is called stop beam time, which leads to the fact that this directory tree is then deleted from the beamline visibility. So if the next user group shows up carrying out their experiment, they get a fresh empty structure, and the data from then and after the experiment has stopped can be accessed only via ACLs from the core file system. Just to give you an idea on what we are dealing, in 2015, we had roughly 200 terabyte a year, 30 terabyte a month. Meanwhile, we have approximately 4 petabyte per year for all beamlines, which is the amount of data being produced. And currently, we have roughly 10 to the 4th of 9 files existing in the core file system. So already a challenge in view of accessing data, storing data, and also data download. And we had to, just because matter of time and money, we had to start to delete data from the permanent disk storage in 2017, which means we just keep it then from then on tape with the option to stage the data back. Currently, the data lifetime and the archiving is that we keep the data on disk for analysis purpose for 180 days after a single beam time has stopped. For visiting users, for in-house research, so I have roughly 14 in-house research teams beside our beamline staff. We have longer hold times on GPFS disk. We remove the data if the capacity runs short in addition. And we have safety measures that we have 2 snapshots a day for up to 21 days to cope mainly with accidentally deleted files by the users so that we can recover it. The data is copied into long-term storage Dcache 7 days after the beam time was stopped, so that we have a safe copy of 2 take copies 7 days after beam time is stopped, at least from the raw data. And before we finally remove it from disk, we create a delta or an incremental that we have the last state of the user data or the in-house data also on tape as well. The data can be requested or stage restored from archive by a request to the experiment control group. And we have some kind of data export and management via the Gamma portal, where we allow the user to manage themselves who has access to the data and also to download the data. So far, we have deleted nothing at the moment, so since the invention of the GPFS. However, there are still open questions for how long we want to preserve the data in the end. Currently, good scientific practice means 10 years. And the question for open access is still under discussion, and we are preparing behind the scenes what to do with it. The Gamma portal, just to illustrate it, it's managed by the DOOR account. We have different views depending on the role, meaning the leader of a project as well as the principal investigator is allowed to manage the data and grant access. We have a basic search ability inside the Gamma portal, and we can enable FTP download with explicit TLS encryption scheme. And in addition, we also offer, assuming we have scientific accounts, data download via Globos, if the user agrees to this. The portal itself has 4 roles: a leader, an applicant, participant, and a collaborator, which are mapped to Unix groups managed by LDAP, regulating the ACL access. For a DMGT group, a participant group, and a CLBT group. Mainly is the leader. There exists only one having the final decision. The applicant who has carried out the experiments. Both of them can add or remove users to the list. They can change the roles of lower hierarchy. They can remove users only of lower hierarchy, and they have read, write, delete to raw, ET, and all other folders. We have the participants, which have read-only permissions in reading the data, and read, write, and delete, and process, share, and scratch. And we have a collaborator role, which only has read access to the data. This system is growing with time. At the moment, each year, we have to enlarge the storage capacity. We have extended the concept also to our other facilities, Flash and Flash 2. We also have special instruments, which are lab sources, where the users like the concept and want to have central-based storage, including archiving capability as well. We have this invented additional schemes in view of live viewer and efficient data transfer, mainly in view of speed, less than in view of access. We have modified the copy procedure, and as said, we started to delete data already in 2017. By deleting, I mean putting it to archive. In addition, we find some more tasks from the users that more and more external users can't even take the data home. They lack storage resources, they lack compute resources, they lack partially analysis software offered by detector vendors because they ship it only with detectors. And staff, as well as our external users, ask for interactive compute resources, as well as for large compute resources, amount of RAM, CUDA cores, GPU computing, faster remote GUI, and exclusive resource usage. And for this, we invented central IT, I have to say, invented the Maxwell cluster concept, meaning an analysis resource, allowing also in-house as well as external users compute capabilities, analyzing data on-site DESY. For this, we invented for our external visiting users so-called scientific accounts, which means external users which are not industry or commercial users, just not to run into conflicts at the moment with software licensing issues. We have invented an own namespace for the users group that we can clearly separate them from in-house. We provide interactive resources in the sense of max or so-called display servers. We have created particular batch resources allowing which are managed by Slurm, a job scheduler, allowing demanding computing for in-house as well as for external users. We have invented additional display servers allowing web-based remote access from outside. And we have remote access to our resources either via tunnel and firewalls, or as shown yesterday, also via FastX and web browser. Just to give you a short idea, on the Maxwell cluster itself, hopefully I still have some few minutes left. The cluster itself provides plenty of compute nodes, some hundreds in total. I own 45 at the moment. At least they are equipped with 256 gigabyte RAM. Each node, and quite a number already offer NVIDIA compute GPU nodes, allowing data analysis for tomography and other special stuff. Lots of software is pre-installed and offers to the user main purpose is high performance computing, offline data analysis for the users, remote visualization, and simulations of all kind.
Andre, I just have to say we have to keep to time, so
yes,
can we take 2 minutes?
This is at the moment what we offer. As said, the FastX server via Remote X, and this, as presented by Andre yesterday, in principle, we broke it down and limited the access by a tailored accession, allowing then the remote access and the remote beamline control for the users. Okay, then I guess I will stop my talk right away with this. I guess things would become too complicated, and then I would like to thank you for your attention.
Okay, thank you very much, Andre. So